Okay, this is an introduction to polar coordinates. So I'm not going to assume we know anything about polar coordinates. So what they are is an alternative system of describing points in the plane. So if I want to describe a point in the plane, I have to tell you where it is in some sense. And what we're used to is what we call the Cartesian system, like the XY system, where I tell you how far to the left or to the right to go, and that's the X value, and I tell you how far up or down to go, that's the Y value, and then you find your point. You know exactly where it is. Polar coordinates are an alternative system of telling you where to find the point. What they tell you is two numbers. It's similar to X and Y. It's two numbers, but they mean different things. Theta tells you basically the direction. We always measure the angle theta off of the part of the x-axis pointing to the right, the positive x-axis. So we measure theta that way, and that tells us which direction the point we're trying to find is. And then we tell you r, which is how far you go in that direction. So that's a perfectly valid way of finding a point in the plane. And that's called the polar system. So first of all, let's talk about how to convert between Cartesian coordinates, which are x and y, and polar coordinates, which is r and theta. I can just look at this picture to tell you what x and y are in terms of r and theta, because I have this right triangle. So, or actually, let me show some work here. If I do sine theta, that's opposite over hypotenuse. So that's y over r. So y is going to be r sine theta. And then similarly, if I do cosine theta in this triangle, that's adjacent over hypotenuse. So x is r cosine theta. So this tells you x and y in terms of r and theta. And then let me write some equations over here that can help you convert the other way. So if I do tan theta, that's y over x. Of course, if x is not 0. If x is 0, then this is undefined. If x is 0, then that means your point is on the y-axis, which means that theta is either pi over 2 and you're pointing straight up, or it's minus pi over 2 and you're pointing straight down. So it's still possible to figure out theta if x is 0. In fact, it's usually easy. But if x is not 0, then you can figure out theta by using this equation. Of course, this has infinitely many solutions. Like if you want to know what theta is, theta could be infinitely many things because you're solving a trig equation. But actually, let me put that on hold. We'll talk about that more in just a second. The other thing I'm going to write in this box is something that can help you figure out r, and it's just the Pythagorean theorem. R squared equals x squared plus y squared. By the way, one thing you should be aware of is that we do allow r to be negative in this system. If r is negative, then instead of going whatever direction theta is telling me to go, I go in the opposite direction. So this is what the picture looks like if r is positive. If r were negative, then I would go that distance in the exact opposite direction. And right, well, that's important to keep in mind as you look at these equations. For example, it's tempting to solve this one for r by doing the square root, and we could, but we would have to consider the possibility that r is negative, so r would be plus or minus the square root of x squared plus y squared. So those are a couple of awkward things about using these equations and also just what polar coordinates are. each point doesn't have a unique representation in polar coordinates. There's infinitely many possible things that theta could be because there's infinitely many solutions to this equation. And there's multiple things r could be because r could be positive or negative when you solve for it here. So let's explore that, I guess. So here's a point whose Cartesian coordinates are given, and we're going to find all possible representations for this point. So picture is not strictly necessary, but let's draw it anyway. Okay, so let's use these equations. X is not 0, so I'm happy using this. So I get tan theta equals 1, and so we should be able to get infinitely many answers for this. First of all, tangent has a period of pi. So first, let me get all the answers for theta that are between 0 and 2 pi. And there's actually still going to be 2 of them because tangent has a period of pi. And I want all the answers from 0 to 2 pi. So one of them is just going to be the arctangent. To solve tan theta equals 1, I can just do the arctangent to get one answer. And that's pi over 4. The way I remember that is just remembering my 45, 45, 90 triangle. So the tangent of pi over 4 is 1. So the arctangent of 1 is pi over 4. Okay, great. There's another answer between 0 and 2 pi because tangent has a period of pi. If I just add pi to this, yeah, let me actually make sure to describe what I'm doing. So these are all solutions from 0 to 2 pi. And then, actually, before I get ahead of myself, these are just solutions to this equation. And we need to be careful as we do this, because one of these actually fits the picture and the other does not, because we have to focus on what quadrant it's in. The point, and this is part of the reason why to draw the picture, although you can easily tell what quadrant it is without drawing the picture, but this is down here. This is, I guess, the third quadrant. Pi over 4 would be pointing up this way, and 5 pi over 4 is pointing down that way. So actually, let me be careful about how I say this. If I take a step back and remember what we're doing, we're trying to find possible polar representations for this point. Keep in mind that r could be positive or negative. If I'm going to go with pi over 4 for theta, that's pi over 4 is pointing this way. That's 45 degrees. Like I measure it off of this, and so I'm pointing that way. That could only make sense if r was negative, because if r was negative, then I would go in the opposite direction, and then I would actually have a chance of landing on this point. So this, yeah, I don't want to say this is wrong, but this could only be right if r is negative. This one, 5 pi over 4, is okay, because pi is 180. This is 225 degrees, which is it's 45 past 180. So I measure starting here, I go 180, and then I go 45 more. That's actually pointing at this point. So this is the angle I would pick if I want a positive r, meaning I actually want to go in the direction that theta is pointing. So both of these answers for theta are usable, but for different r's. Okay, yeah, I need to be careful about how I say this, but so let's find r. R squared is like that, so that's 2. So r is plus or minus 2. I am making silly mistakes, but I think I'm fixing them all. All right, let's just write our answer because I think we're good. It goes r first and then theta. So r could be positive root 2, and I'll pick the value of theta that goes with a positive r, plus any multiple of 2 pi, of course. That's the other thing that can happen with polar coordinates, is because theta is an angle, I can give you a silly angle that's way bigger than 2 pi, which tells you to just go around and around the circle a bunch of times. So we have to, since I'm trying to do all possible polar representations, I have to take that into account. So, well, I did. The other possibility is minus root 2, and the value of theta that goes with a negative r, of course, plus any multiple of 2 pi. Maybe I didn't need to clarify that so much, but k could be any integer here. It's any integer multiple of 2 pi. And that's all possible representations. All right. So let's talk about curves defined by polar equations, because of course we've talked a lot about curves defined by Cartesian equations, where you have an equation involving x and y, and then we graph it. So now we can have that, but in polar. So we'll have an equation involving r and or theta, usually both of them, but we're going to start with some simple examples. And these have graphs. Okay, so these are easy. These kind of illustrate situations in which polar coordinates are actually useful. So circles centered at the origin are really easy to describe. If I just tell you r equals 2, that's all the points that are distance 2 away from the origin, because r is just the distance from the origin. So the hard part is actually drawing a circle, but yeah, let's call it good. Okay, so that's what you do if r is just equal to a constant. It's just a circle whose radius is whatever that number is. What if your equation tells you theta equals a constant? So we have some particular value of theta. Well, we just have to remember what theta is. To find a point that has theta equal pi over 6, I would just measure an angle of pi over 6, which is 30 degrees, by the way. So, yeah, maybe that looks about right. So I measure an angle of pi over 6, and then r could be anything. So I'm talking about all the points on this line. Of course, r could also be negative, which would give me the points down here. So this is a line that goes forever in both directions. And of course, the hardest part is actually drawing a straight line. Okay, so these were two simple curves. Let's talk about one that's a little bit less simple. So this is an equation that involves both r and theta. It's r equals sine theta. And you can actually graph these. This isn't a terribly practical thing to do by hand, but we'll sort of do it. You can plug in values of theta and see what you get for r. So I did that for a few of them. Sine of 0 is 0. Sine of pi over 4 is root 2 over 2, and so on. This isn't going to produce a great picture, but it's good to watch me do. So when theta is 0, r is 0. R is 0 is just this point. Actually, for this point, it wouldn't even matter what theta is. If r is 0, then we're just talking about this point. When theta is pi over 4, I get root 2 over 2. So root 2 over 2 is about 0.7. So pi over 4 is 45 degrees, so I'm pointing in this direction, and I'm going out a distance of about 0.7. So I'm going to say it's like there. Pi over 2 and 1, so pi over 2 is 90 degrees, so I'm pointing straight up there, and I go a distance of 1, so that's easy to find. 3 pi over 4 is this way, and then I go out a distance of 0.7 again, so maybe about here. And then pi is pointing this way, but this is 0 again, so I'm just back to this point. And actually, I could keep going. If I just keep going up by pi over 4 every time, I could fill in some more numbers. The very next one would be 2 pi, so sine has a period of 2 pi, and so we would just be tracing the same curve over and over again. But actually, let me fill in these. So 5 pi over 4, maybe I'll be quick about this. The sine of 5 pi over 4 is minus root 2 over 2. So for 5 pi over 4, that's this way. But the r value is negative. So actually, we're just talking about this point again. We covered this point twice. When theta was pi over 4, r was positive root 2 over 2, because pi over 4 is pointing this way, and r is positive, so we go that way. When theta is the exact opposite value, meaning 180 degrees off of that, so 5 pi over 4, the value of r is it's the same absolute value, it's just that this one's negative and this one's positive, so actually I just find this point again. And actually 3 pi over 2 is just going to find this point again, because sine of 3 pi over 2 is negative 1, and so I would be pointing down that way, but r is negative 1, so I go the opposite direction, so I just cover this point again. And then the next value of theta is just going to cover this point again. Okay, and sorry. I meant for this to be x and this to be y, of course. This is a normal plane. So we're going to connect these dots somehow, but actually let me gather some more information before I do it. Let's talk about the next example. We're going to take this same curve, r equals sine theta, and convert it to Cartesian. So we're going to get an equation involving x and y. So to do that, we basically have these equations. And I'm trying to do r equals sine theta. So here's the smoothest way to do this. There's a couple of things I like to see. I like to see r squareds, because whenever I see an r squared, I get to replace it with x squared plus y squared. I also like to see r, if it's not squared, then I like to see sines or cosines attached to it. So here's one thing I can do to just sort of make what I'm looking at look better. I kind of, well, either I want this to be an r squared or I want there to be a sine or a cosine attached to it. And this, I would be happy if this said r sine theta. So actually, I'm just going to multiply both sides by r. And now I have clear things to replace everything with. X squared plus y squared, that's the same as r squared. R sine theta, that's the same as y. So now I have an equation with only x's and y's and no r's or thetas. So I've done my job, but the purpose of me doing this was to help me draw this picture. So actually, let me work with this equation just a little bit more. I have some tricks like completing the square that I can do. So I get all my x's and y's on one side. This is already a perfect square. I'm not going to mess with that. I can make this a perfect square. So I am going to add a number that makes this a perfect square. And the number that I pick is half of this coefficient squared. So in other words, I'm adding a fourth. And I can't just do that unless I do it to both sides. So I just added 1/4 to both sides. Okay, I'm going too slow probably. But this is a perfect square now. In particular, this is y minus 1/2 squared. So why did I just do that? So I can recognize this curve. This is the standard form of a circle. This is a circle centered at, this is like x minus 0, so the x-coordinate of the center is 0, and the y-coordinate is 1/2, and the radius, ooh, let me be careful about using the letter r. This isn't really r like polar coordinates are, this is just the radius of the circle. The radius of this circle is 1/2, because r squared is 1/4. So going back to these dots I was going to connect, this is supposed to be a circle, which actually it already kind of doesn't look like one, but that's my fault for not being a perfect artist. This is, I mean, it doesn't look that far off, but it'll be a little bit of a wonky circle. But this is supposed to be a circle centered at this point with a radius of 1/2. So it's not the worst circle I've drawn in my life. So yeah, that's the graph. I like this example because it does illustrate how when you're graphing equation defined by polar coordinates, the negative r's do come into play. Like when we plotted these points, we had to consider negative values of r, and for us it wasn't that weird because we found that the negative values of r were just sort of retracing what we already drew, like what we already drew from 0 to pi, and then when we kept going past pi, it was just retracing what we already drew. Also, this is an equation that has a nice description as a circle in Cartesian coordinates. Anyway, let's do another one kind of like that. So here's another equation with r's and thetas. We're going to convert this to Cartesian coordinates, and then we'll use that to identify the curve. I could graph this the way I did the last one, like make a chart for values of theta and just find secant theta for each one and plot those points. I'll skip that for this one. We'll end up having a good description of this curve anyway. So, what do I like to see? First of all, I'm not crazy about secant. Looking at the equations that I use to convert, there's no secants anywhere. I like sines and cosines, so maybe the first thing I'll do is change this to cosine. And then now I'm going to think about how I like my r's to appear, and there's two ways I like my r's to appear, either an r squared. That makes me think, what if I multiplied both sides by r? If I multiplied both sides by r, I would like this side, but I wouldn't really like this side so much. I don't know what to do with r over cosine theta. So maybe I shouldn't make this an r squared by multiplying by r. The other way I like to see r's is attached to a cosine or a sine. And actually now I see an easy manipulation I can do. If I just multiply by cosine, then I get that. And that's something I like to see. So r cosine theta, I can just replace that with x. So this is actually just a vertical line.